Hello dear friends, welcome my channel. Today's discussion is compactness. Let x comma tau be a topological space and a subset of x. Let G denote be a family of subsets. Must remember friends, G denote a family of subsets of X. G is called cover of A if a subset of union of G such that G belongs to G. If every member of G is an open set, then cover G is called open cover. If there exists G1 subset of G1 subset of G and such that G1 is a finite set and cover of A, then G1 is called a finite subcover of G. Let x comma tau be a topological space and A subset of X if there exists finite subcover of a cover G of A is said to be reducible. A finite subcover of a cover G of A is said to be reducible to finite subcover. Is said to be reducible. Let x comma tau be a topological space and a subset of X. A is said to be compact set if every open covering of A is reducible to finite subcovering. This equation is very important. A subset of U union of G and G such that G belongs to G. Let x comma tau be a topological space. Let G denote a family of open subsets of X. Then G is called an open cover of X and X equals to union of G such that of G belongs to G. Let x comma tau be a topological space. Let F denote a family of subsets of X. F denote a family of subset of X. Then F is said to have finite intersections property. If there exists F1 is subset of F such that F1 is finite, intersection of F such that F belongs to F1 does not equals to phi. For a closed and bounded subset of R, every open covering admits a finite subcovering. Every open covering admits a finite subcovering. Another statement, a closed and bounded subsets of R is compact. A closed and bounded subset of R is compact. A topological space S, tau is called Lindell of space. A topological space x, tau is called Lindell of space if every open cover of X is reducible and to countable cover. It follows from the above definitions that every compact space is Lindell of space. Every compact space is Lindell of space, but the converse is not true. Every x, d is Lindell space where X is any infinite countable set but it is not compact. X comma D is Lindell of space. Must remember Lindell's of space where X is any infinite countable but it is not compact. So every Lindell of space x comma tau is Lindell of space. Every open cover of X is reducible. So it follows the definition, above definition, that every compact space is Lindell of space. Every compact space is Lindell of space, but converse is not true. This is the very important. Every compact space is Lindell space, but converse is not true. Let x comma tau be a topological space and X belongs to capital X be arbitrary, then X is said to be arbitrary, then X is said to be locally compact. X is said to be arbitrary and X is said to be locally compact at X if the closure of any neighborhood of X is compact. X is called locally compact if it is compact at each of its point but need not be compact as a whole. What is locally compact? Locally compact set is that if the closure of any neighborhood, friends, I have already told what is closures. Closures of any neighborhood of X, okay, is compact. X is called locally compact if it is compact at each of its point. Alternative definitions: a topological space x comma tau is locally compact if each element of X belongs to capital X has a compact neighborhood. Locally compact need not be compact. A closed and bounded infinite subset. A closed and bounded infinite subset of R contains a limit point. A closed and bounded infinite subset of R contains a limit point. Bolzano-Weierstrass theorem. A matrix space x comma D is said to be a sequentially compact. Sequentially compact if every sequence in X has a convergent subsequence. The set of all real numbers in 0, 1 is not sequentially compact. For this sequence in 0, 1 convergence to 0 belongs to 0, 1. On the other hand, 0, 1 is sequentially compact. A sequence xn belongs to capital X such that n belongs to capital N is said to be convergent if xn tends to x0. Friends, I just want to discuss brief discussions, because each and every locally compact I need to explain a lot of, but I do not explain so much. I just read total theory and total gist, because I just abbreviate all of the compact space, and when in the examination you can learn, you can just listen this total, you just listen this video. It is very helpful for examination. That's why I create this kind of. Otherwise one topic need one video, like locally compact need another video. Every topic has need another a video, but I just discuss very briefly. Okay, friends, if x comma D be a matrix space and A subset of X, then the statement that A is compact A is countably compact, A is sequentially compact, A is sequentially compact are equivalent. So if x comma d be a matrix space A subset of X, then the statement that A is compact. A topological space x comma tau is said to countably compact if and only if every countable tau open cover of X has finite subcover. Compact, that implies it is countably compact, has finite subcover. Next, a matrix space x comma d is said to have Bolzano-Weierstrass property if every infinite subset of X has a limit point. In brief, the phrase Bolzano-Weierstrass property is written as BWP. A space with BWP is also called Fachet compact space. A space with BWP, also called Fachet compact space, Bolzano-Weierstrass property. And let x comma d be a matrix space, let epsilon greater than 0 be any given real number. A set A subset X is called an epsilon net if A is finite, and X is union of S epsilon A and A belongs to A. The matrix space X comma D is said to be totally bounded if it contains an epsilon net for every epsilon greater than 0. Here number 2 implies that given any point P belongs to X, there exists at least one point A belongs to A such that dPA, then distance of rho and A less than epsilon. Let Gi such that I belongs to del be an open cover for a matrix space x comma d. A real number del greater than 0 is called a Lebesgue number for the cover if any A subset X such that dA less than del, and that implies A subset of Gi0 for at least one index I0 belongs to del. Lebesgue covering lemma, every open covering of a sequentially compact space has a Lebesgue number. Let x comma tau be a topological space and A subset X an open cover G of A is called basic open cover if all the open sets of the cover are contained in some given base. An open cover G of A is called sub-basic open cover. Sub-basic open cover if all the open sets of the cover are contained in some given open subbase. A topological space YU is said to be embedded in topological space X tau if YU is homeomorphic subspace of x comma tau, and furthermore if x comma tau is compact, then Y is called compactifications. Sorry, spelling is wrong. Compactifications. Spelling is compactification. X comma tau is compact, then Y is called compactifications of X, and let x comma tau be a topological space, let G and G1 be two open covers of X, then G is said to be a refinement of G1 if and only if any G belongs to G and there exists G1 belongs to G, thus that G subset of G1. A space X is said to be a paracompact if and only if every open cover of X has a locally finite open refinement, that is a refinement which is locally finite open cover of X. Next, every indiscrete every indiscrete space is compact. Let x comma tau be an indiscrete space, then tau is equal to phi comma x, and consequently the only open cover of X is X, which is finite cover since it consists of only one member X. Hence X is compact. Any infinite subset of discrete topological space is not compact. For example, let x comma tau be a discrete topological space and let a subset of X be an infinite set. To prove that A is not a compact set, by definition of discrete topology, every finite subset of X is open and hence A is open and A belongs to X. Write A equals to, theory is very important. Must remember every indiscrete space is compact and any infinite subset of discrete topological space is not compact. This kind of questions is asking in CSIR NetGate only for short and another university will ask very short note. So clearly A is open cover of A. Evidently A is infinite set and hence any finite subfamily of A is not a cover of A, showing thereby A is not compact. Every topological space x comma tau is compact if X is finite. Number 4, R comma I is compact and R comma D is not compact where I and D are respectively indiscrete and discrete topology. R comma U is not compact where U is being usual topology on R. Any open interval is not compact. Important result: a closed subset of compact space is compact, that is x comma tau be a compact and a subset of X be closed, then A is compact. Number 2, let A comma U be a subspace of x comma tau and then A is compact with respect to the topology U, and if and only if A is compact with respect to topology tau on X. A countably compact topological space has a Bolzano-Weierstrass property. Number 4, a countably compact topological space has a Bolzano-Weierstrass property. A closed subset of countable compact space is countably compact. If x comma tau is a compact topological space, then every basic open cover of it is reducible subcover. Every cofinite topological space x comma tau is compact. A topological space is compact if every basic open cover has a finite subcover. A continuous image of a sequential compact set is sequential compact, and x comma tau is a compact that implies each family of closed sets with finite intersections property has a non-empty intersections. A topological space is compact. Every class of closed set every class of closed sets which has empty intersections property has non-empty intersections. Number 11. Suppose A is a compact set in a regular space x comma tau and G subset of x is a neighborhood of A. Then there exists a neighborhood V subset of x such that V bar is subset of G. V bar means V closure. And let A be a compact of regular space x comma tau if G is an open subset containing A and A subset of H subset of G. A contains H and G contains H. H contains A and G contains H. Compact every compact regular space is normal. A compact Hausdorff space is normal. A compact Hausdorff space is normal, or if A and B is disjoint compact subsets of Hausdorff space X, then there exist open sets G and H such that A subset of G and B subset of H. A compact Hausdorff space is regular. A compact Hausdorff space is closed. Let A and B be a disjoint compact subsets of a Hausdorff space is closed x comma tau. Then there exists disjoint open sets G and H such that A subset of G and B subset of H. A topological space x comma tau is a Hausdorff space if and only if disjoint compact subsets of X can be separated by disjoint open sets. A continuous image of a compact space is compact. A compactness is a topological property, that is f such that x comma tau tends to y comma u is a continuous map. Then any compact set A subset of X and Fa is subset of Y is compact. 20. Number 1. A closed and bounded subspace of R is compact. Every closed interval A comma B is compact. Number 3. Cantor set is compact. Cantor set is given by gamma intersection of n equals to 1 to n and f n. N is the index f index n, and where f index 0 is equal to 0 comma 1, f index 1 is equal to 0 comma 1 by 3, union of 2 by 3 comma 1, f2 is equal to 0 comma 1 2 by 9 comma 1 by 3, union of 2 by 3 comma 7 by 9, union of 8 by 9, and 1, so on. F index n is the union of second disjoint closed intervals, each of the length 1 by 3 to the power n, and being finite union Fn is closed. Also, gamma is bounded as gamma subset of 0 comma 1. A subspace y comma u1 u index 1 of Ru is compact, and if and only if y is bounded and u is closed, a continuous real valued function whose domain is closed and bounded interval of R attains its supremum and infimum, or a continuous real map of a compact space into any metric space is bounded. A compact metric space is separable if a matrix space x comma d is totally bounded, then x is bounded. Every total bounded matrix space is separable. A matrix space is sequentially compact if and only if P. Every compact matrix space has a BWP, Bolzano-Weierstrass property. A countably compact topological space has Bolzano-Weierstrass property. Every open cover of sequentially compact matrix space has a Lebesgue number. Every sequentially compact matrix space is totally bounded. Every compact subset of a matrix space is closed and bounded. A matrix space X that implies matrix space X is sequentially compact. A matrix space is Lindelöf of space if it is second countable. A matrix space is compact if and only if it is totally bounded and complete. Every compact matrix space is complete, and a matrix space is x comma d is said to be complete if every Cauchy sequence in X is convergent at some point in X. Now friends, I have told all the property and all the definitions of compact space. I think that if any students will study this property, they can easily it is very helpful to remember everything. We should remember it is very helpful for all mathematics students. So now we will start. Let x comma tau and y comma u be topological spaces, and let fx comma tau tends to y comma u and be a continuous map and a compact subset of X. Show that Fa is compact and show that compactness is a topological invariant. Now I will prove only one theory, because all the I just discuss all the theory, but I do not prove any theory. Just only one theorem I will prove in this video. This video is helpful for the remembering all the theorems of compact space and all the short note, because it's this type of in case of CSR, NetGate and other competitive examinations, they will ask very simple questions, but you have to remember, otherwise you can forget. If you will not remember these definitions, you can get trouble in examinations. Now I will prove this theory. So let f such that x comma tau tends to y comma u be a continuous map and let A be a compact subset of X, and to prove that Fa is compact. Let G index alpha such that alpha belongs to del be an open cover of A if a subset of union alpha belongs to del and G alpha, from which G alpha means alpha index, from which a subset of if inverse if a subset of if inverse u alpha belongs to del G alpha index equals to union of alpha belongs to del F inverse that is a subset of union alpha belongs to del F inverse G index alpha. Taking F inverse G index alpha and O index alpha X subset of union alpha belongs to del. Since F is continuous, so F inverse G index alpha equals to O index alpha is open in X. Then equation 2 shows that O index alpha such that alpha belongs to del is an open cover of which is known to be compact, and hence this cover must be reducible to a finite subcover. Say O alpha j index alpha j such that 1 less than equals to j less than equals to n. Clearly a subset of union I equals to 1 to n O index alpha I alpha j, from which f a j equals to 1 to n f O alpha j f O alpha equals to f inverse G alpha subset of G alpha, that is f O alpha subset of G alpha, and therefore union J equals to 1 to n f O alpha j set of union 1 to n G index of alpha I, making, so friends, I just give a numbering that fa is equal to this portion is 1 number, equation number 1, and this portion is 2, portion is 3. Making use of equation number 3, we get f alpha is equal to I equals to 1 to n G alpha I. This proves that G in such that 1 less than equals to I less than equals to n is an open cover of Fa. Thus, an arbitrary open cover G index alpha such that alpha belongs to A of Fa is reducible to a finite subcover G index alpha I such that 1 less than equals to I less than equals to n, showing thereby Fa is compact. Thanks for watching.